Okay, 4 things. Number 1, and most importantly, we are going to go through step by step in this lab exactly how greens powders are made. That means chopping, pressing, drying, separating, measuring, milling, concentrating, measuring again, conditioning, atomizing, and testing. And if you don't know what those are, don't worry, we're going to go through each one of them step by step. The second thing we're going to do, you've almost certainly never been told this, but there are 2 distinct types of greens powders. There's whole leaf and there's juice powders. And if you're going to buy these powders, you need to know the difference. That means how they're made, and we'll make both of them. We'll go through step by step, why they're priced the way they are, and key nutritional differences, and we'll cover all of that. Number 3, at the end of this video, you will have close to everything you need to decide for yourself whether greens powders are right for you. You won't need a nutritionist or a dietitian or a doctor to tell you if they're okay. You will be able to decide for yourself. Finally, I'll finish up by giving you my opinion on which I think is better, whole leaf or juice, and also what to look for when buying or consuming a quality greens powder. Okay, let's get started actually making these things. We're going to do both whole leaf and juice side by side. We're going to use spinach as our example, and our first step is chopping. Okay, we have 17 pounds of spinach that we're going to process, and the first step is chopping. Chopping isn't always necessary, but it is a common practice in industry because it can significantly increase product density. Increased product density leads to more product on a truck. More product on a truck means lower per pound shipping costs, and lower per pound shipping costs means food is cheaper and everyone wins. Now, for our purposes, denser product means we can get more spinach into our dehydrator and thus a higher yield of dry product per dehy session. I also think that chopped product will allow us to get more life out of our juicer, but that's probably a bit more speculative. Now, some of you may be wondering why chopping increases density, or given a fixed volume, how chopping can put more mass in said volume. Well, chopping does 2 things to increase density. So the first thing chopping does is it breaks the cell walls within the leaf and stem. Now, water was contained within the cell walls of the entire leaf and was confined to that given space, or its given space within the cell. When chopped, that water is released and can flow freely. So think of it like holding 2 water balloons side by side. You're likely limited on how you can arrange them in a given space, but the moment you pop them, you can put them in almost any position you like. So the second thing chopping does is it removes air between the leaves. Because of the shape and structure of spinach leaves, there is a ton of air that sits between them, and this air naturally takes up space, or better put, it occupies volume. Now, when we chop it, we allow more freedom of the plant parts to move, and thus air between chopped product is significantly reduced. So again, think of this like taking an empty gallon of milk before you throw it away. You'll typically squeeze the jug to push all the air out, which then allows the plastic to be pressed together. And the result is that the jug now takes up less space in your trash can. Well, the same principle applies to our chopped spinach, albeit it's a little harder to notice. Here you can really see the density increase that we've achieved on our spinach. You remember the 17 pounds we had on the table at the beginning. We processed 16 pounds, we chopped 16 pounds, but it's really apparent here that we've increased our density fairly significantly, probably around 3.5 times, and we've got it all here in this bucket, in this container. Okay, so we basically finished up chopping, and you'll notice here that I'm taking some samples. In food production generally, it's always good to take samples throughout your process, specifically at each unit operation if you can. That way, if you ever have a contamination, allergen or pathogenic, you can go back to that specific point and identify if the contamination occurred at that specific processing point. Okay, if we were only making a whole leaf powder, we'd be almost done. We'd simply add the chop to our dehydrator, mill it, and call it a day. But we're making a juice powder, which is much more difficult and time consuming. I do also want to add some of what is removed from our product during juicing to the dehydrator. That way you can really get a full picture of these products, what they are, what's removed, what's in them, etc. All right, on to juicing. We're using a screw press type juicer as it best replicates a Vincent press, which is used at scale. Someday I'll do a demonstration on a benchtop Vincent press, but for now this Angel juicer will work. Now there are certainly some differences between a traditional screw press and this juicer, but this press is going to work by rotating gears against each other, whereby our spinach leaf will be in the middle and will undergo increased pressure as it moves down the line. Okay, so I mentioned earlier why that chopped may be better for our press. It may give it a longer life. Here's kind of some of my thinking on why that might be. Number one, you've got an increased surface area on your chopped versus your whole leaf. So think about like wood chips. When you're starting a fire, you're going to be able to get a flame started much easier with wood chips versus the log. The same process for extraction of juice applies here. With chopped, there are just more avenues for juice to exit the plant versus whole leaf. Another reason is reduced resistance. Basically, the press is going to chew up, so to speak, our spinach, and by chopping it, we've taken a step away from the press. We've given it a head start. In general, though, any pre-processing we can do will probably yield improved extraction efficiency, and so most likely a longer working life for our juicer. Now on yield, the best we can hope for is about a half a pound of juice per pound of fresh. So we've got about 8 pounds to a gallon. That means starting with 17 pounds of fresh, we can expect a little over a gallon of juice. Our juice falls out this end, and our pulp, or press cake as it's called in industry, falls out the other end. What we have coming out this end is significantly weighted toward fiber. There will certainly be small amounts of protein, sugars, vitamins, minerals, etc. And actually one day we'll do a nutritional analysis of some pressed plant material. I think it would be fascinating to actually see a detailed breakdown there, but as you might guess, those analyses are few and far between. You can find all the nutritional info you want on orange juice, but not much in the way of nutritionals on orange juice pulp. But let's at least talk about fiber, which is the majority of this press cake. Specifically, spinach fiber is about a 2-to-1 ratio of insoluble dietary fiber to soluble dietary fiber. A few years ago, we did a fiber analysis on a winter garden variety of spinach, and on a dry basis, it came out to about 26% dietary fiber, whereby about 64% of that was insoluble and 36% was soluble. I believe 90% of your insoluble is going to be a combination of cellulose and hemicellulose, while your soluble is mostly pectin. Anyway, enough about fiber. There's an endless amount we can say about it. Oh wow, what a flattering angle of my face. I can't imagine why more people don't film themselves this way. Okay, that whining that you hear, that annoying squeaking sound, it is, it's an indication that it's time to stop the juicer and reset a little bit. But basically there's a buildup of product of spinach on those gears, those twin gears on the angel juicer, but specifically inside of the grooves. They're caught in the grooves on that juicer, and that's why you hear that humming noise. We are done juicing / pressing, and it's time to centrifuge. And as a reminder, food production is always a mess. So gonna clean up this space real quick, and then it will be on to separation or centrifuge. It's worth looking back at where we started and what we have now. We started with some whole leaf chopped, which is there on your left, and we separated it into juice, which we've got the better part of a gallon, and then we've got some fiber, or some press cake as it's called in industry. Okay, the following stage involves separation. This is where it starts to get fun. To produce a juice powder that dissolves fully in water, it's essential to remove substances from the juice that aren't water soluble. For the fruit and vegetable variety, this primarily means removing fiber. This bowl-like object that you're looking at, this is the rotor. This is where all the separation between the liquid and the pulp occurs in the centrifuge. And I want you to see it now because it's clean, and it's not going to look that way here soon once we get moving on separation. Now, our juicer does have about 1 to 3 millimeter screens that give us some decent separation, but our fiber is going to get much smaller than that, and if we really want to remove it completely, a filter isn't going to cut it. We instead need to use a centrifuge. A centrifuge is a device that uses a central or centrifugal force to separate components of a mixture based on their density by spinning them at high speeds. For our purposes, we are going to use it to rapidly accelerate the process of sedimentation. Most of us are fairly familiar with sedimentation. One example is sand settling on a shore. So think about some sand getting kicked up within the water on a shoreline. For a while, there's a cloud of sand within the water, but eventually the sand settles fully back onto the ocean floor. Specifically, sedimentation works by gravity and requires both a continuous phase and a dispersed phase. We want to remove the dispersed phase, which is a combination of fiber and to a lesser extent proteins, vitamins, and minerals. We want to remove this phase, which is dispersed in our continuous phase, hence the name dispersed phase, from our continuous phase. Now, our continuous phase is a homogeneous mixture of proteins, vitamins, minerals, and then thousands of other dissolved compounds. In order for an effective and efficient separation, you want these phases to have different densities. And if you do, your dispersion obtains sedimentation velocity, or the forces acting on your dispersion are such that the continuous phase will become wholly distinct, i.e. separate from the dispersed phase. That is, you'll eventually obtain separate layers of both your liquids and your solids. We can use a centrifuge to rapidly accelerate sedimentation. Specifically, our juice flows into a rotor spinning at about 6,000 RPM, revolutions per minute, generating forces roughly 3,500 times greater than that of gravity. This spinning creates a centripetal force which keeps our juice moving in a circular path. However, due to inertia, our mixture wants to keep moving straight. So think about being in the middle of a bench seat in a car with a piece of paper while making a sharp turn. During that sharp turn, you're going to slide down the bench and get pushed up against the car door. Meanwhile, that piece of paper probably will have moved very little, if at all. During the turn, your body tries to keep going straight due to inertia, but the car door forces you into the turn. Now, you can imagine that while you're pushed up against the car door, the piece of paper is still resting in the middle or close to the middle of the bench. The reason for the separation between us and the piece of paper boils down to inertia. We have more mass than the paper and thus more inertia, and we resist that change in motion more than the paper. Our mixture is much the same and contains different densities. Denser components like the pulp have more mass and thus more inertia, making them resist the circular motion more strongly than the lighter components like our juice. So what ends up happening is your denser, heavier fiber takes a wider path within the rotor. It moves straight longer before the walls of the rotor can redirect it. Our less dense, lighter juice takes a more narrow path around the rotor, and we see a distinct separation between the two. Now, the rotor can only hold so much liquid, and eventually, depending on your GPM, gallons per minute, unclarified liquid will flow into the top of the rotor and push your clean liquid into an external cavity. From this external cavity, it can flow to a clean port where it's collected and now fully clarified. Alright, this is my VFD, variable frequency drive. I use this to control the speed of the motor that turns the rotor in the centrifuge. VFDs are used a ton in industry. They basically allow you just to control how frequent a motor turns. Okay, my liquid is starting to have flow issues, and this is really why I need a peristaltic pump. So on the last part of this separation, I'm always constantly adjusting the valve and the bucket in order to not overflow the centrifuge. The centrifuge is rated at about 10 gallons an hour, and normally my flow rate's fine for that, but if I open the valve too quickly, I can definitely, at least for a second or two, exceed that 10 gallon per hour flow rate. And if that's the case, then I'm going to not get full separation in some of my products. So I've got to be really careful here. It took a lot of spinach to get this juice, so I am going to make sure I can clean as much of it as I can. So I've transferred the remainder in the bucket to this beaker, and I'm just manually pouring it through a funnel into my centrifuge. All right, now we're setting up our tubing to catch our unclean liquid that's sitting in the rotor. This is just liquid that didn't make it to the clean port, and we should have roughly 200 ml or so. Okay, that rotor started off pretty clean. Let's open the centrifuge top and see what it looks like inside. And here is your spinach pulp stuck to the walls of the rotor. Now that we've finished, let's quickly polish our juice using this 300 mesh filter. Okay, I just showed you how the clean juice flowed right through the filter. Well, here you can see the difference in how a quote uncleaned juice behaves. Essentially, it can't move easily through the filter because it builds up rapidly due to significantly increased solids content. This also gives you an idea of how using a filter to clean product would not be a feasible first step, but as I mentioned previously, more of a polishing step. Here we get a really good overview of what we've done with the centrifuge. We have our clean, fully clarified spinach juice there on the left. We have a small beaker of the unclean. This is basically just the juice that we started with, and then we have the pulp that we pulled from it. Okay, that is separation. Let's move on to basic drying. Okay, what I want to do here is begin a demo showing you exactly what you're getting when you take greens powder. For example, if you add a teaspoon of spinach powder to your morning smoothie, how much spinach is that exactly? That is the question we will answer with this demo, and in the future, you'll be able to get a really good sense of how much raw greens you actually consumed when using any greens product. So how do we do this? Well, we're going to start with whole leaf spinach. Most people consume spinach in leaf rather than shot form, and we're going to measure out a true USDA serving of spinach. So what is a USDA serving exactly? Well, for spinach to count as a single serving of vegetables, you must have 2 cups of it. Now these are loose cups or 30 grams by weight. We're going to densely pack this beaker to over 60 grams, and that will give us, by the USDA standards, a single serving of vegetables. The final step is to dry, and then after that we can determine the weight of our dried serving. Now, for convenience sake, we're going to dry our chopped rather than our leaf because we can get more in the dryer and it's easier to manage. But as a reminder, by chopping, we increased density of our spinach, but we didn't concentrate it any further. I'm telling you this so you know that 65 grams of whole leaf is the exact same as 65 grams of chopped. Let me say a little bit more about drying in general. Dehydration at scale is a modern marvel. It's allowed us to take food that lasts from 1 to 3 weeks to potentially indefinite shelf lives. Not only does it remove water and reduce shipping costs, and thus the cost of food itself, but it also limits pathogen activity by eliminating the medium in which pathogens proliferate, i.e. water. Technically, the USDA defines dehydrated foods as those with less than 2.5% moisture, but in practice, everyone says dehydrated. Drying of foods boils down to heat and mass transfer. Specifically, we're trading with our food heat for mass. We supply the heat, in return, the food evaporates moisture or loses mass. The challenges here are twofold: getting the heat in and getting the water out. And of course, there are many different ways to dry, some extremely expensive, some pretty reasonable, but needless to say, drying technology is something that is constantly being worked on, refined, and improved. Now, for our purposes, we're going to use two different types of drying methods. One, which we're using now, I will explain the other one later. The first is a standard dehydrator. It uses a heating element and a fan. This heating element supplies the heat, the fan ensures even dispersion of said heat, and this turns out to be an extremely simple yet effective way to dehydrate our spinach. Alright, in addition to the 65 grams that we just weighed out, we are also going to dry some of the samples we took immediately after chopping. Okay, the dryer is loaded and we are ready to start the dehydration process. Chlorophyll, or the compound that gives spinach its nice green color, it will start to degrade, break down, lose its color at about 140 degrees Fahrenheit or 60 degrees Celsius. So we're going to dry well below that at 115 F for about 46 C, and that is going to give us a really nice margin of safety on obtaining a good looking product when we're all said and done. Okay, drying is done. Let's look at what we've got. And here's our cup of spinach. And here's our pulp, which is mostly fiber. And just remember, anytime you juice or use juice powder, you are giving virtually all of that up. Okay, let's get on to milling and/or particle size reduction. Before we mill anything though, I want to get a weight on our dried serving size. And it looks like we're at about 6 grams. We can thus say that 6 grams of dried spinach is equivalent to about 65 grams of whole leaf raw spinach. Or better put, a serving of spinach in dried form is about 6 grams. I'm going to combine our USDA serving with the remainder of what we dried, and then when we're completely finished milling, I'll show you that serving again in powdered form. Here I'm using a basic tabletop grinder with a single blade. We're going to mill our whole leaf first and then our fiber taken from our pressed juice. On our milled whole leaf, we should expect to see a particle size of roughly 150 microns, or a little over 1/10 of a millimeter. I'll show you some more close-ups of this soon, but for now this looks really nice and we can take a sample. Fiber, on the other hand, is much harder to mill, and so we're looking at double to potentially triple the particle size on our finished milled fiber, or up to 1/3 of a millimeter. Once again, let's collect a sample. All right, let's take stock of where we're at post-milling. On the left there, you have your whole leaf product, and on the right, it's just the fiber pressed from the leaf when we were juicing. At the top on the left, you've got your chopped, which is wet. In the middle, you got your chopped, which is dry, and then you have what we just milled, your whole leaf spinach on the bottom. On the right, you've got your pressed, which is wet, and then we've got it dried in the middle, and then on the bottom, that's your milled fiber. Okay, finally, let's observe what one serving of vegetables, in our case greens powder, looks like in dried and powdered form. And there you have it. That is a full serving of vegetables by the USDA standards, dried and in powdered form. Now, there's still a bit more we need to go over. Specifically, I want to explain juice powders to you. But if you're looking at whole leaf powders, you can now start to decide for yourself if these are right for you. If you have a scale at home, you could use the range of about 5.5 to 7.5 grams for greens powder, and that's going to give you close to / more than a full serving of vegetables. And if you don't have a scale, hopefully this helps you at least eyeball it to an extent. Okay, now we can move on to our Brix tests. All right, now that we have a fully clarified juice, we need to get a sense of what's inside it. Or better put, we need to measure the solids content of our solution. Now, knowing solids content can help with concentrating, as we'll discuss later, but it can also help with using carrier agents like maltodextrin, and I will demonstrate using maltodextrin. But just to make sure this is clear, some of you might be thinking that this is a liquid. How are there solids inside the liquid? Well, the solids within the liquid are fully dissolved, or put differently, they are completely water soluble, so you can't see them. At any rate, we are going to measure our solids content with a Brix meter. So how does a Brix meter work? Well, a Brix meter, also known as a refractometer, measures how light bends through a liquid, and based on that reading can give a value of the solids / sugar content contained within the liquid. So our Brix score tells us just that. It's the percentage of the solution that is solids. Okay, here we're going to measure the solids content of our cleaned, centrifuged, non-rotovapped spinach juice. So we should roughly 6% solids within our solution. That means if we have 100 ml of our solution, which is close to 100 grams, then within that 100 ml of juice, 6 grams will be solids. Or if we could somehow extract those solids and have them isolated, which is what we're going to do, then we would have material that would be able to fully dissolve in something like water. Okay, now let's set up our rotary evaporator. What does it accomplish? Well, rotary evaporation allows us to concentrate our solution by evaporating a portion of the liquid in our mixture. So if you think about adding water to a fruit juice to lessen the sweetness, what you've done is you've reduced the amount of sugar content per milliliter of water. You've diluted it. Well, this is the reverse. We're removing some, but not all of the water. And when we're done, we'll still have a liquid, or in our case, spinach juice. It's just going to be a more concentrated version than what we had after clarification. Okay, let me walk you through our rotovap system and how it works in general. First, we have our ice bath where we have cold water that is moved by the blue and white pump through our condenser. This cold water creates a cold space for our vapor to condense, hence the condenser. The cold water, after it has made it all the way up and then back down the condenser, recirculates back into the ice bath where it can be pumped out again. As our evaporation flask rotates and liquid evaporates, vapor from our liquid moves through the vapor duct and hits our condenser where it turns back into a liquid and drops into our solvent flask. This induction motor aids the evaporation process by turning the flask anywhere from 1 to 60 RPM. This rotation creates a thin layer of liquid on the surface of the flask, enabling more rapid evaporation. Now finally, this black tubing is connected to our vacuum pump, and our vacuum pump evacuates air from our system, enabling evaporation of our liquid at much lower temperatures. And that is the basis for our system. All right, so why are we doing it? Well, number one, rotovaps are cool and they're worth seeing. But for our purposes, rotary evaporation is going to allow us to get more out of our spray dryer, our next step. So when we spray dry our post-rotovap liquid after this, we're going to see a higher concentration of dried solids per milliliter of liquid. For example, our initial Brix test showed that our solution after clarification was about 6% solids. So then, for every 100 milliliters of clarified spinach juice, we will have about 6 grams of spinach juice powder. Now that assumes roughly a 1:1 gram to milliliter ratio. But when we evaporate a portion of the liquid in our spinach juice, the solids don't go anywhere. In fact, they just occupy more of the juice left behind. Thus, if we concentrate our spinach juice to say 15% solids, we will get about 2.5 times more solids per milliliter of liquid from spray drying than we would have from our unconcentrated juice. Concentrating also allows us to increase glass transition temp, or TG. Now, glass transition is fairly complicated, but suffice it to say that TG is the temp at which our product goes from hard and glassy, or you can turn it into a powder, to soft and rubbery, or it turns to junk. Now, when we increase solids content and decrease moisture, we can raise our glass transition temp significantly and raise the probability of getting a product we're showing. There's definitely more to concentration and its effects on spray drying, but that's enough for now. Okay, to recap, our goal at this stage is a concentrated solution which will make spray drying easier. what exactly makes a rotovap well suited for this task? Well, there are two things. There is rotation and then there is a vacuum. Our evaporation flask is constantly rotating. This constant rotation within a circular motion will create an extremely thin layer of liquid around the surface of the flask. This layer, due to all of it being directly exposed to our heated water bath, can evaporate extremely quickly. If you wanted to get a better sense of this, think about two pots of water with equivalent volumes. One is very tall and skinny, the other is short and wide. The short and wide one will have nearly all of its water exposed to a stove burner, while the tall and skinny one will have only what's on the bottom of the pot exposed. Obviously, when you visualize this, you can see that due to the increased surface area of the short pot, or all of its water being exposed to the stove burner, it's going to evaporate quicker than the tall pot, and this is exactly what we're doing with our rotovap. The other aspect is our vacuum. The vacuum pump allows us to reduce pressure within our system, and this reduction in pressure allows for a lower evaporation point. For example, in your kitchen, if you want to boil water, you're going to have to heat the water to 100 C or 212 F. However, under reduced pressure, we can significantly decrease that boiling point. Now, in our system, we'll reduce pressure to about 100 millibars, where water will boil at roughly 116 F or 47 C. The advantages of this are obvious. Because we can evaporate our water at lower temps, we can maintain the nutritional integrity of our products while processing them, i.e., we don't destroy them by overheating. Okay, we're ready to start rotovapping our juice, i.e. concentration. This is 2200 ml, which is just over a half gallon. Here I'm adding some water to my tubing to prime my pump head. That is, when I start pumping, I don't want the pump to run dry. It's not good for it and it could damage it. So I'm adding some water before I start the process to prime it, so to speak. And we have water circulating at this point, so we are ready to turn our vacuum pump on and evacuate our system. On our water bath, which heats the E-flask, we're shooting for about 115 F. Our temp range, it's in Celsius, so 46 C will do fine. And now we'll turn on our induction motor, which rotates the E-flask. And all things being equal, faster rotation is going to mean faster evaporation. Alright, we've set our rotation speed. Let's raise the water bath and begin evaporation. Notice our E-flask is filling up with bubbles. This is called bumping. Essentially, the product undergoes rapid boiling due to decreased pressure or a temp that is too high. And I don't have any bumping stones, so I'll have to monitor my vacuum very closely throughout the process. And if I'm not careful, my juice can end up boiling over into my solvent flask. At this point, the bumping is finally settled, but it's taken upwards of an hour, and I've had to monitor it like a hawk, constantly adjusting rotation speed and our vacuum level. Okay, now that we have the bumping settled down a bit, we're finally starting to evaporate, and you can see it here where our condensation is dripping back through the vapor duct into our solvent flask. You can see from this view our bumping has virtually disappeared, and so now I'm comfortable increasing our rotation speed in order to accelerate evaporation. Here again, you can now really see that layer of liquid on the inner surface of the E-flask. Okay, our solvent flask is really starting to fill up. Let's quickly check our parameters. Our water bath is at 46 C, just under 115 F, and we're maintaining a vacuum of 80 millibar. For context, water boils at 212 F at 1 atmosphere of pressure, or just over 1000 millibar. However, in our system, with the pressure significantly reduced to about 8% of atmospheric pressure, the boiling point of water is substantially lowered, close to 108 F. So, by creating this vacuum, we've nearly halved our boiling point. So at this point in the process, I'm not satisfied. I'd like to evaporate a few hundred more ml. But a few of my kids are down the hall unsupervised, so I actually have to stop the process temporarily. But for now, let's look at what we have and do a quick Brix test. Okay, I want to check and see what we've evaporated in this first leg of the process. And it looks like about 1000 ml. And as a reminder, we started with about 2200 ml, so we've reduced the volume of our solution by about 45%. The next question is, how does this reduction in volume affect our solids content, or how concentrated has our spinach juice become? Let's do a Brix test to see exactly how much we've concentrated our solution. And remember, we started at about 6% solids. So this test is showing 8.75%. That equates to us increasing the concentration of our solids content by about 60%. Thus, in the first leg of our process, a 45% reduction in the volume of our solution resulted in a 60% increase in the concentration of our solids content. Alright, as I said earlier, I wanted to get a bit more concentration out of our juice, so I did a secondary rotovap trial. However, I should note that before I started again, I sampled off about 200 ml of our 8.75% juice to slightly speed up the process. I was aiming to remove about 500 ml from our 1000 ml of 8.75%. Let's see how we did. And we did close to perfect given that goal. We reduced the volume of our juice again, this time by 50%. Let's check our new Brix. Observing Brix is one thing, but look how the juice sits on the sides of the beaker after it's swirled. The thickness and viscosity have become pretty apparent, and we're at roughly 17%. For purposes of spray drying, I'm going to use a juice that is closer to 15% concentrated, and as you might have already guessed, if you want to dilute a sample after rotovapping because maybe it's too viscous or it's just higher concentration than you want, you simply add the proportionate amount of water back in until you get the desired concentration. Here you can really get a sense of what we removed during evaporation. Now, we did pull off a small 200 ml sample, but remember, this beaker on the right was full, and now we can fit all of our juice into the beaker on the left, which is a quarter of its size. And here's another view showing our concentrated beaker of juice, as well as the water in total, also sitting in beakers, removed during evaporation. Okay, before we start spray drying, we're going to condition our solution a bit using maltodextrin. You've probably seen maltodextrin on the back of an ingredient label and wondered what it's doing in your food. Maltodextrin is a mild-tasting starch extracted typically from corn, but could also be rice or potatoes, and it can do a lot in the world of food processing. For us, though, it acts as a carrier when we're trying to extract powder from liquid. That is, using maltodextrin is another method, in addition to rotovapping, that can increase our solids content and improve our TG temp, allowing us to have a usable and flowable powder after spray drying. I have a 500 ml sample here, which means based on about 6% Brix, I have about 29.5 grams of solids content within the sample. I'm going to shoot for about 40% maltodextrin on a dry basis. That means I will need between 17 and 18 grams of maltodextrin to achieve that percentage. Alright, on to spray drying, and again, we can thank the milk industry for pioneering another technology in food production. Dairy started using spray dryers in the 1900s to make milk powder, and today spray dryers are used to make all kinds of things from instant coffee to formula, juice powders like what we're doing here, active ingredients in pharmaceuticals, cosmetics, detergents, dyes, etc. The working principles here are fairly simple. We have atomization, dehydration, and separation. Let's start with atomization. The word atom itself is derived from the Greek word atomos, which means uncuttable or indivisible. So while an atom is not an indivisible portion of matter, when we say atomization, we're thinking minuscule. That is very, very small droplets of water, or in our case, spinach juice. Now, in order to atomize our juice, we're going to use compressed air. Specifically, we pump our solution into a spray nozzle in combination with said compressed air. This mixture of pressurized gas and green juice results in extremely tiny droplets, which can then be dried rapidly in our drying chamber. The key factor in atomization, if you haven't already guessed, is an exponential increase in surface area. That is, by breaking up our solution into smaller and smaller droplets, we're exposing more and more of our liquid to hot air. After you've atomized, dehydration becomes much easier. You can imagine that when surrounding tiny droplets of your solution with air and heat, drying can happen fairly quickly, and that's exactly what occurs within our drying chamber of our spray dryer. Small droplets are pushed into this drying chamber, and they're being propelled by air that is anywhere from 200F to 300F in temp, and the result is rapid drying. Finally, our dried product needs to be fully separated from our water vapor, and this is where our cyclone comes in. At this point, our water vapor and solids go their separate ways. The cyclone allows your solids to fall into a collection flask like this, while your vapor is expelled in the opposite direction. And that is spray drying in a nutshell. Okay, here's a great view of our spray pattern. This looks really nice, and we're definitely just about ready to start spray drying. Okay, first up we are doing straight spinach juice. Before we start though, I need to briefly explain how we can control the kinetics of our drying process. We essentially have 3 variables under our control. 2 we control directly and 1 indirectly. First is our inlet temp. This is how hot we want our drying chamber to be. Second is our feed flow rate. Faster feed flow, given fixed atomization pressure, means larger droplets of our liquid. If we have larger droplets of liquid, it's going to be harder to dry them given a constant temperature. It's these two variables that directly impact our outlet temp, where we get some secondary drying. Our inlet temp sets a basis for overall temp, and our flow rate affects the level of drying. That is, if less liquid is flowing into our drying chamber, given a fixed temp, droplets get more exposure to surrounding air. In essence, there is more heat to go around, and so, if there is more heat to go around, the air exiting our system is going to be warmer. Okay, let's start trial 1. We are going to be drying straight spinach juice, no carriers, no concentration. We are going to have an inlet temp of 150 C. We're going to have a feed flow rate of 220 ml per hour. And we are going to have a target outlet temp of 80 C. We have a good inlet temp, and it's time to start pumping our juice. And I should just note here that within about a minute of our feed entering the atomizer, we're going to know pretty definitively if this is going to be a successful trial or not. This is already a bad sign. We are seeing a lot of product in our collector, and our collection flask is still pretty clear. It would appear that we've exceeded glass transition temp and that this trial is a failure. Let's try again. All right, on to trial number 2. We are going to add 40% maltodextrin to our spinach juice on a dry weight basis. We are going to have an inlet temp of 150 C, a feed flow rate of 220 ml per hour, and a target outlet temp of 80 C. All right, this is a good looking spray pattern we have here. We are ready to start pumping our juice. And right away, this looks a lot better than trial 1. We have minimal buildup in the collector, but more importantly, we're starting to see that collection flask change color. It's starting to collect product. So notice this green spot building up on the chamber wall. Every trial, the spray biases on one part of the chamber on the glass. It could be the same as before, or it could be different. And I don't really know why this is, but I thought it was at least interesting to point out. And again, we have minimal buildup in our collector, and we've got a really nice buildup of product in the collection flask. Already, I'm way happier with this trial compared to trial 1. As you can tell, the biasing on that side of the drying chamber, it's becoming way more pronounced. Okay, you'll notice here that product isn't really collecting on the wall of that flask, of that collection flask. It's more sticking to it, which is not a good sign, as you might guess. Won't tell you yet how the trial ends, but that's a pretty good hint. All right, even though I mentioned that the trial isn't going as well, given the caking on the side of that collection flask, this gives you from afar a pretty good view of what a successful trial looks like. Again, minimal buildup on the collector, and the collection flask itself is building up with a nice green color, the color of whatever it is you're drying. This looks good from afar, and if I didn't know any better, I would say it is successful. All right, even though we kind of know how this trial went, let's at least take off the flask, the collection flask, and take a look. Here are some close-ups of what I was able to obtain from the collection flask, and as you can tell here, this just doesn't look very good. It's hard and it's sticky, clumps. There is some moisture on the inside of the product, so it's not a fully dried product. This just isn't a good usable product. You can't put this in a smoothie, or you can't mix it with anything for that matter, at least not in a convenient way. So trial 2 unfortunately is a failure. Let's move on to trial 3. All right, on to trial number 3. We now have a 50% maltodextrin concentration in our spinach juice. We've gone from 40 to 50, so that's a 25% increase in maltodextrin. We've got an inlet temp of 150 C, feed flow rate cut in half at 110 ml per hour, and a target outlet temp of about 90 C. During this trial, I pay a lot closer attention to the buildup within the collection flask. Basically, I want to ensure a more natural accumulation rather than caking, and that's exactly what you're seeing here. At this point, I'm very confident in our drying kinetics and that this trial is going to yield good results. Okay, let's look at the results of trial 3. Here is a view into the bottle, and you can really tell, as I mentioned earlier, there's a nice buildup of product on the side of the flask, within the flask. This is absolutely usable. Let's get it out and actually take a look at it. I want to give you a sense of how unbelievably fine this powder is. When I rub it onto my fingers, it spreads like a paste, but it's a powder. In regards to particle size, most particles here are probably in the range of 1 to 10 microns. to give you a sense of size, the width of a human hair is on the order of about 100 microns. This means that our juice powder here is about 10 to 100 times smaller than that. All right, on to trial 4. And the question here is, can we successfully spray dry some spinach juice without the use of a carrier? So we're going to use our concentrated juice, which is about 14.5% solids, on a number of different inlet temps. We're going to dry at 150, 125, and 105. So trials within a trial, if you will. Our feed flow rate will still be the same at 110 ml per hour, and we'll have a few different target outlet temps at 85, 85, and 75 C. Let's see what we can come up with. All right, here's the collection flask at 150 C, and at first glance it looks pretty good. It looks all right, but when we remove it to get a better look inside, we're going to see it's not what we want. It's caking, just as it did in trial 1. So we're going to start this over at 125 and see if we can do better. And here is the inside of the flask at 125C. It's still not what we want. It is better. It's hard to tell from this view, but it does handle a little bit better. It's still not quite what we want. So we are going to take our temp down to 105C and see what happens. All right, this looks really good, and I'm pretty happy with this. And really though, there's not much we can do. At 105, I wouldn't feel comfortable going any lower. I don't think it's going to be very efficient drying lower than 105. So we're going to let it ride out and see what we end up with. And we are nearly finished. Time to wrap this up and see exactly what results we have from the 105 trial. And we have finished with the 105 sub trial. And here's the inside of the bottle. Already scraped it, but it looks really nice. And I'll give you a better shot of this in the lab. I at least wanted you to see it here after we were done. Here it is in one of my kids' baby food jars. Forgive the poor focus. It's nearly midnight. I've been at this since 8 a.m. I'm pretty wiped out. I'll give you a better shot of this in the lab though, but we have really solid results. All right, let's go back to the lab and look at these results a little closer. As a recap, the bottle on our left held our successful trials, that's trial 3 and trial 4, and the bottle on the right got nothing from trial 1 and caked product, which is still there from trial 2. This one on your right is your maltodextrin treated powder. This one on your left is your Rotovap. These bags, I mean, when I say right and left. And you'll notice a little color difference, significant color difference really between the two. That really boils down to me degrading some of that chlorophyll with too high of a Rotovap temp at about 140, and didn't do myself any favors there in maintaining color, but also learned that 140F for an extended period of time definitely going to harm the color on your greens. But these are 2 usable powders, flowable, one treated with maltodextrin, one concentrated by rotovapping. Okay, I want to do a final demonstration that I think will really drive home the differences between whole leaf and juice powders. What I'm going to do is add a small amount of these powders back to liquid so you can get a sense of their very real differences. We'll do all 4 powders that we obtained: whole leaf, fiber, Rotovap juice, and maltodextrin juice. Okay, first up, maltodextrin, and yes, these are urine cups that I'm using. They're perfect for holding samples because they're small and they're sterile. Next, our whole leaf spinach. Here is our Rotovapt sample, and now on to our fiber. Okay, so notice with the Rotovapt and maltodextrin, you can see right through it. It's basically a uniform mixture, a clear juice, if you will. The fiber, on the other hand, is kind of an oil and water scenario. You can see all of the fiber settling to the top and moving within the liquid, and there is very little, if any, that constitutes with the water. The whole leaf, on the other hand, and in my opinion, really shows you what you're missing with the juice powders. You've got everything in the juice and fiber, plus the smaller and likely more soluble fiber we took out during centrifuge. To me, this looks like something healthy and full, while the juices look light and a bit sterile. The fiber probably is pretty good on its own, but it's going to be more of a challenge to mix and consume. All right, we've done a lot within these processes, and I think it's worth looking back at all of our samples in various stages to get a sense of the overall scope of these products. All right, very glad that's over. Let's do a little wrap up. First point, if you're trying to process thousands of kilos or pounds an hour at scale, you're going to do everything you can to run on a continuous basis, meaning that theoretically you could run 24/7. As long as you've got products, inputs to feed, you can continue to have outputs. That's opposed to batch processes where you put product into a piece of equipment and then you just wait for it to get done. And then you add more at the end of that batch. At scale, you want to run as much continuously as you can. Freeze drying is an example of a batch process. That's one where at scale, there's really no way around it. You're going to have to run in batches. Everything I showed you can be run continuously at scale, except for the conventional hot air dehydrator and the rotovap. At scale, those are going to look a little differently. So if on hot air dehydration at scale, if you want to run that continuously, you're going to use something like a rotational dehydrator where you'll continuously feed product into that dehydrator, as opposed to just like a box that you put product in and wait for it to finish. If you're concentrating, you wouldn't use a rotovap. You would use something like multiple effect evaporators where you can evaporate in stages, more like in a continuous process rather than in one single batch. Another thing to keep in mind is you just saw how juice powders and whole leaf powders are made. You know there's a distinct difference. But as far as I'm aware, there's no actual legal definition by the FDA standards of a juice powder. So there's a good chance you're going to see product out there that is labeled as a juice powder but is actually whole leaf. Now, there is a way you can tell for sure. So remember, we removed the fiber from the product to make a juice powder. So if the product is a juice powder, you should see minimal to no fiber in there. So use this as an example. On a whole leaf basis, you're going to see about 20 to 30% fiber on a dry weight basis. So if you've got 10 grams of whole leaf powder as a serving size, on an ingredient label, you should see 2 to 3 grams of dietary fiber. If, on the other hand, that same product, that 10 gram serving size is actually a juice powder, you should see less than a gram. You should see virtually no fiber in that product. And that's how you can know for sure. Now, a lot of products out there will have juice powder on the label and they're blended with other ingredients. You're not going to know either way on that. But if it's standalone, that's a good way you can figure it out. Just look at the fiber content. All right. At the beginning of this video, I mentioned that at the end, you would have everything you needed in order to make a decision as to whether or not greens products were right for you. Well, there's one thing I've yet to bring up, and that is knowing the sourcing of the products you're considering buying. Or to put it more specifically, when you're considering a product, knowing specifically where the ingredients within that product came from. Do everything you can to try to buy ingredients from quality sources. The US is a great source. There are other good sources in the world, but the US is a great source. Whole leaf and juice powders are often priced very differently in the market. You need to know that if you're considering purchasing one or the other, so let's look at why that is. All right, let's use an example. Let's say we start with 100 grams of fresh spinach, and we can sell that 100 grams at 1 cent per gram. All right, so that gives us $1 if we sell all of our fresh spinach, given 1 cent per gram. Instead, let's say we have the option of selling that fresh spinach as either a whole leaf powder, we'll dry it down into a whole leaf powder, or we'll spray dry it down into a juice powder. We can do either one. So if we want to sell it as a whole leaf powder, our reduction factor, what we start with and what we end with, is about 10 to 1. And we showed that in our example. So we start with 100 grams of fresh spinach, we dry it using a conventional dehydrator, and we have 10 grams of whole leaf powder, or 10 grams of whole leaf. We're no longer going to sell that for 1 cent per gram. We would take a 90-cent loss on our potential sell. We're going to now sell it for 10 cents a gram if we want to match what we could have gotten on a fresh basis. All right. Now, the reduction factor for fresh to juice powder is a lot higher. It's about 20 to 1, and this 10 to 1 for whole leaf and 20 to 1 for juice powder. This is actually how they play out at scale. And the reason it's higher for juice powder is because we also removed the fiber. So it's 20 to 1 for juice powder. So if we start with 100 grams of fresh and we want to sell it as a juice powder, that means we are going to have 5 grams of juice powder when it's all said and done. Well, again, we're not going to sell this for 1 cent per gram. We take 95-cent loss on our sale. Instead, if we want to match that sale of fresh at $1 in total, we're going to sell it for 20 cents a gram. And you can see how this plays out in practice. just looking at the difference between our juice powder and our whole leaf is the juice powder is twice as much as the whole leaf. And this is what you're going to see a lot of times when you're buying it, is juice powder is substantially more expensive than whole leaf, oftentimes way more than twice the amount. It could be 3, 4, 5 times the amount. And you need to know that when you're actually looking to purchase these products in the market. Okay, we've talked about pricing differences between whole leaf and juice. Let's look at what distinguishes these two products nutritionally. For the most part, we've already seen it. It primarily comes down to fiber. One has fiber removed, one has fiber intact. And when we think about the term dietary fiber, that term can largely be credited with Dennis Burkitt. Dennis Burkitt was a surgeon working in Africa, and in the 60s, he hypothesized that the reason there was such a lack of obesity, heart disease, diabetes among Africans was that they had more abundant fiber in their diets as opposed to the West. So I'm guessing his thinking went something like, in the West, food is highly processed, and in that processing, we remove the fiber, and fiber is no longer consumed to the degree it once was, and disease is rampant. On the other hand, food is minimally processed. If at all in Africa, fiber is kept intact, it is consumed, and there is a lack of the same disease among native African populations. You hear the term dietary fiber thrown around a lot, but funny enough, there's actually no universally agreed upon definition of dietary fiber. It's for a few reasons. One, there's a lack of consensus on which carbohydrates should be included within the definition, as well as physiological effects. Different fibers have different physiological effects, so there's a lack of agreement there. And then there's not a universally accepted method for quantifying dietary fiber within a foodstuff or potential foodstuff. In terms of classifying fiber, fiber used to be thought of as either soluble or insoluble, and you'll still probably hear dietitians and nutritionists talking about it that way. There was also this belief that if the fiber was insoluble, then it could not be fermented in the large intestine. As to the first point, biochemists are finding that this is way too simplistic. Fiber should really be classified on its degree of fermentability. That is, these things, fiber, it should be thought of really more on a spectrum rather than a binary. And then to the second point, they actually, through advanced imaging techniques, have found that insoluble fiber can be fermented in the large intestine, albeit to different degrees and at different rates. As far as health benefits go, there are a lot, and I think more will continue to be discovered over time. I'm very, very bullish on fiber. But I think a good way to think about fiber today is not just on a laundry list of health benefits, but in terms of a few different groupings. So I look at fiber as a limiting agent, a catalyst, and a regulator. So as far as a limiting agent goes, it limits, fiber helps you to feel more full. It limits the amount of food you're going to intake. So for example, it takes many oranges to make a jug of orange juice. You could go through 2, 3 glasses of orange juice really easily and consume, 8, 9 oranges, at least the caloric amount of those oranges. But if you instead just wanted to eat the orange whole, you're probably going to get to 1.5 or 2 oranges before you're like, I'm full, I don't want to eat anymore. And it's because that fiber is helping you to feel more full. It also it moderates the absorption of glucose and lipids, sugar and fat, just contributing to better overall metabolic health. It acts as a catalyst within the digestive system in that it stimulates the production of short-chain fatty acids, all kinds of benefits being found with short-chain fatty acids, and it promotes the growth of beneficial gut bacteria, which enhances both immune function and gut health. And then finally, it's just a great natural regulator of digestive processes. It helps to move waste through your system as well as prevent constipation. As to my opinion on which I think is better, I'm definitely biased towards whole leaf. But bias aside, I would bet any biochemist that has taken seriously the study of plant fiber and dietary fiber generally would absolutely be telling you you should do everything you can to get more fiber in your diet. So the thing is, for most people, when they're trying to get healthier or lose weight or have a more nutritious diet, protein is so often the macro they're trying to maximize. And that's all well and good. I think for most people, trying to get more protein is it's a really good goal. But it can also be really hard to maintain and hit consistently. Oftentimes they're looking at making sure they hit 25 to 40 plus grams of protein per meal per day. And that can be really tough to maintain, to hit that target consistently. But with fiber, most nutritionists would tell you, hey, just try to get an additional 15 grams per day. Depending on how many meals you eat, that might be 5 to 7 grams per meal per day. And for most, that's incredibly feasible. So I guess the question I would ask is, given both the short-term and long-term benefits of increased fiber intake, combined with how easy it is to get more fiber, why wouldn't you want to do that? Why would you look for any option that removes fiber, i.e., why would you choose a juice powder over a whole leaf if your goals are just general wellness? So again, I'm biased, but I believe when it comes to choosing a greens powder, you should absolutely go with the whole leaf over the juice. We've been over a good bit of info on pricing and nutrition, comparing both the whole leaf and the juice, but forget those for a moment and just look at the two side by side when they're mixed with water. To me, the juice powder looks a bit sterile and kind of thin, whereas the whole leaf, it's got a richer, more complex, just overall healthier look. To me, it just passes the eye test. And remember, Dr. Burkitt's hypothesis was that this extreme processing of food was leading to disease. Well, could we not argue that using almost 17 pounds of spinach to make just one jug of juice, and then spinning that juice at roughly 3,000 times the force of gravity is not extreme processing? And for the record, I'm not against juice powders or even processed foods. I love white bread and Oreos. They're delicious. But I don't eat those things for a health benefit. Likewise, most people consuming greens powders are looking for a general health benefit. And so to me, the choice between whole leaf and juice powder is abundantly clear. Now, maybe your goal isn't general wellness. Maybe you're after a natural source of beta carotene. Well, in that case, I can definitely see why you'd opt for a juice powder. But as it relates to general wellness, then in my opinion, whole leaf is absolutely the way to go. Okay, let's sum everything up. If you can find a premium source of greens powder, US-based preferably, whole leaf, and you consume 5 to 7 grams of that a day, then not only are you getting more fiber, a much needed nutrient in the US and the West overall, you're going to get a full serving of vegetables by the FDA standards. I think that's pretty cool. I'm a huge fan of greens powders, but they have to be the right greens. They have to come from the right place. Okay, I hope you've enjoyed this. I hope you've gotten something out of it. That's going to be it for today. We'll see you on the next one. Take care.